Imagine standing in the middle of the Sahara Desert, nothing but scorching sand, brutal heat, and absolute silence stretching for thousands of miles in every direction. No water, no life, just endless, merciless gold. Now imagine, buried beneath your feet, one of the greatest feats of human engineering ever conceived. A network of pipes so massive, so mind-bending in scale, that it could circle the entire Earth twice. This is not science fiction, this is not a movie, this actually happened. A group of visionary engineers looked at the world's largest, driest desert and said, "We will bring water here." And then they did it. Today we're going inside the most ambitious water infrastructure project in human history, the Great Man-Made River, the artificial river that split the Sahara in two. Stay with me, because what these engineers pulled off will absolutely blow your mind. To understand why this project exists, you need to understand the crisis that made it necessary. Libya, a nation roughly 4 times the size of France, is 95% desert. The Sahara doesn't just nudge at its borders, it is Libya. Temperatures regularly exceed 50 degrees Celsius. Rainfall in most regions, less than 25 millimeters per year. For comparison, London gets 600 millimeters annually. And for millions of people living there in the 20th century, fresh water wasn't a luxury. It was a daily fight for survival. Libya's coastal cities were growing fast, agriculture was struggling, and the Mediterranean Sea offered no easy solution. Desalinating seawater on a national scale was too expensive. Importing water was unsustainable. Something radical had to happen. Then, in the 1950s, while oil prospectors were drilling across the Libyan desert, they discovered something even more valuable than oil. Vast underground aquifers, ancient lakes of fresh water trapped beneath the Saharan rock, some dating back 10,000 years to a time when the Sahara was green. Billions and billions of cubic meters of water sitting perfectly still deep beneath the sand. The question was no longer where the water was. The question was, how on earth do you get it out? The answer came in 1983 when Libya's government launched what would become the single most expensive construction project ever attempted on African soil. A project budgeted at over 25 billion US dollars. But the real challenge wasn't money, it was geography. Engineers had to connect 4 major underground basins, Kufra, Sirte, Marzouk, and Hamada, spread across a desert the size of India. Satellite imaging and geological surveys revealed the scale of what they were dealing with: 4 separate aquifer systems, each hundreds of meters below ground, each separated by hundreds of kilometers of sand and rock. The planning phase alone took years. Teams of engineers, Libyan, Korean, European, American, mapped every inch of the pipeline route. They calculated water pressure across elevation changes that spanned entire mountain ranges. They modeled soil compositions, seismic risk zones, and thermal expansion of materials in extreme desert heat. Every decision had consequences. A miscalculation in pressure could rupture a pipe buried 30 meters underground. A poor route choice could mean a 200-kilometer detour through impossible terrain. The planning rooms were filled with mountains of blueprints, geological core samples, and engineering arguments that went long into the night. The final design, a pipeline system stretching 4,000 kilometers, supplying up to 6.5 million cubic meters of water per day to cities along the Libyan coast. But the real challenge was still ahead. How do you build something this big in the middle of the Sahara? You start with concrete, enormous amounts of it. Each individual pipe section of the Great Man-Made River was made from pre-stressed concrete, reinforced with high-tension steel wire, wound tightly around the core. Each section measured 4 meters in diameter, wide enough to drive a truck through, and 7.5 meters long. Each one weighed 75 metric tons. The project ultimately required over 530,000 of these sections. That's not a typo. To manufacture them, engineers didn't ship the pipes across the desert. They built pipe manufacturing plants directly in the Sahara, massive industrial facilities rising out of the sand like alien cities, equipped with their own concrete mixing systems, steel winding machines, and curing chambers. At peak production, these plants were churning out hundreds of pipe sections every single day. But pipes alone weren't enough. To pull water from aquifers hundreds of meters deep, engineers needed pumping stations powerful enough to push millions of cubic meters of water uphill across vast distances. These stations were equipped with multi-stage centrifugal pumps, industrial giants capable of generating enormous pressure, driven by diesel and electrical systems purpose-built for desert environments. And then there were the pre-stressed anchor systems, the expansion joints designed to absorb the 40-degree daily temperature swings, the protective coatings to prevent internal corrosion, and the computerized monitoring systems that would eventually watch over thousands of kilometers of pipe in real time. How could engineers possibly make all of this work together in the most hostile environment on Earth? Construction began in 1984, and what followed was an exercise in organized chaos on a biblical scale. The desert became a construction site the size of a small country. Thousands of workers, engineers, welders, machine operators, laborers, descended on remote regions of Libya, living in temporary camps that had their own kitchens, medical centers, and communication systems. The first challenge was trenching. Before a single pipe could be laid, enormous trenching machines had to carve a channel through the desert floor, typically 2 to 3 meters deep, wide enough to accommodate the massive pipe sections. In areas with soft sand, the walls of the trench would collapse almost as fast as they were dug, requiring constant shoring and stabilization. In rocky terrain, and much of the Libyan desert is hard, compacted rock, controlled blasting was used to break up the ground before excavation machines could move in. The sound of explosions echoed across empty desert valleys day after day. Then came the pipe laying itself. Each 75-ton section was transported by heavy lift vehicles across terrain with no roads, no infrastructure, and temperatures that regularly melted rubber. The sections were lowered into the trench using giant cranes carefully aligned and then joined with rubber-sealed steel collars designed to handle ground movement without cracking. The precision required was extraordinary. A misalignment of just a few centimeters in a joint could mean a leak buried 30 meters underground, undetectable until thousands of liters had already been lost. Special challenges emerged constantly. Desert winds buried newly laid trench sections overnight. Flash floods, yes, even in the Sahara, destabilized sections of completed pipeline. Equipment broke down in the heat, waiting weeks for replacement parts to arrive. Yet kilometer by kilometer, the silver ribbon grew, cutting across the sea of gold like a vein of life through stone. Phase by phase, the pipeline crept north from the deep aquifers toward the thirsty coastal cities. But even with the pipes in place, the hardest engineering problem was still unsolved. Here's where it gets truly fascinating. Getting the water out of the ground is only half the battle, moving it 4,000 kilometers across a desert without losing it. That's the real engineering masterpiece. The system works in stages: deep well fields, some containing over 1,000 individual wells, draw water from the aquifers using powerful submersible pumps. The water rises to the surface and enters collector pipelines, which feed into the main transmission system. From there, booster pumping stations, spaced at regular intervals along the pipeline route, keep the water moving with consistent pressure. Without these stations, friction and elevation changes would slow the water to a crawl, or stop it entirely. The system is monitored by a centralized SCADA control system, supervisory control and data acquisition, which tracks pressure, flow rate, and water quality at thousands of points simultaneously. If a pressure anomaly is detected anywhere along the 4,000-kilometer network, operators can isolate that section remotely within minutes. Water quality is maintained through sedimentation tanks and filtration systems located at key nodes in the network. The ancient aquifer water arrives naturally clean, filtered through hundreds of meters of rock over thousands of years, but additional treatment ensures it meets drinking standards before reaching homes. One of the most remarkable aspects of the system is its gravity-assisted design. Wherever terrain allows, engineers routed the pipeline to use gravity to help move the water, reducing the energy needed by the pumping stations and making the entire system more efficient. The result is a flow of water so consistent, so reliable, that it has been compared by the people who drink it to a miracle. Before any section of pipeline was declared operational, it went through rigorous testing. Engineers used hydrostatic pressure testing, filling completed pipe sections with water at pressures far exceeding normal operating levels to identify any weak joints or microfractures before they became catastrophic failures. Ultrasonic testing devices were deployed along sections to detect internal cracks invisible to the naked eye. Flow meters were calibrated and recalibrated. Pump outputs were measured against design specifications. Pressure gauges were tested for accuracy at extreme temperatures. Every valve, every joint, every seal received individual inspection. When issues were found, and they were consistently, engineers adapted. Some pipe sections were relayed, some pumping configurations were redesigned, some monitoring systems were upgraded. This iterative process of test, fail, learn, and improve was baked into the project from the beginning, and it's what made the difference between a project that works and one that fails catastrophically in the desert. Today, the Great Man-Made River delivers 6.5 million cubic meters of fresh water per day to Libyan cities, including Tripoli, Benghazi, and Sirte. Water that irrigates farms, fills homes, and sustains millions of lives. Agricultural land that was previously dust has been transformed into productive fields. Citrus groves, wheat fields, and vegetable farms now grow in regions where nothing grew before. The economic impact runs into billions of dollars annually, but the human impact is even more profound. For families who once rationed every drop, reliable running water changed everything. For farmers who gambled each season on rainfall, consistent irrigation changed everything. The United Nations called it the eighth wonder of the modern world, and standing beside it, watching fresh water flow silently through pipes buried beneath the Saharan sand, sand, it is impossible to disagree. This is what human ingenuity looks like at its absolute peak, a problem so enormous it seemed impossible. Engineers who refused to accept that answer, and a river, artificial, invisible, buried, that brings life to one of the most lifeless places on Earth. A silver ribbon cutting beneath a sea of gold, carrying hope across the desert.